And this was a point that Gödel made in a letter that he wrote to John von Neumann 70 years ago when he said, he asked him what today we would immediately recognize as the P versus NP question. And he said, if there really were a fast algorithm, like let's say a linear or a quadratic one, it would have consequences of the greatest magnitude. It would mean that the mental effort of the mathematician could be completely replaced by machine, apart from the postulation of axioms. Okay, so this is sort of the stakes of the question, right? It would also have implications for AI. I mean, you may know that enormous amounts of money are being poured right now into the problem of building giant data centers to train neural networks to sort of solve one particular NP problem, which is given this neural net like GPT, O3 or whatever it is, and given this training data, find the setting of parameters in this neural net that minimizes the loss, that makes this neural net do the best at predicting this training data. Right? This is how modern AIs are created by spending massive amounts of computing power to train them, which means to find better and better solutions to this optimization problem of setting the parameters of the neural net. Okay, if P equaled NP, that would mean that you just had this super fast, essentially perfect solution to that problem.
Is there a connection between solving some of these like traveling salesman or like energy minimization problems and training a neural net? So for example, there's a lot of like either quantum or analog computer type work to
Yeah,
solve, I would call it like Ising problems or energy
yeah.
minimization problems. If you get very good at those, do you get very good at training neural nets by some kind of, proxy?
The answer is yes, you do. Okay, but in order to explain why, we don't really need to say anything about analog computing or anything like that, right? We just need to talk about NP-completeness, okay, which was sort of the central discovery that really started modern theoretical computer science, in the early 1970s. Okay, so I explain what's the P versus NP problem, right? But now the surprising part was that it turns out that of all the NP problems that people want to solve, a huge fraction of them turn out to encode the entire difficulty of the class NP. Okay, meaning that these are problems that are sort of at least as hard as anything else in NP, right? If you could solve any one of these problems in polynomial time, then that would mean that P equals NP. Okay, that's what it means for a problem to be NP hard. That it sort of encode, that every problem in NP can be reduced to it. Okay, and if an NP hard problem is also itself in NP, then we call it NP complete. Okay, that's what these terms mean. Okay, and so what was discovered in 1972 or three was that actually most of the optimization problems that people really care about, including the traveling salesman problem, including bin packing, including a clique, which means if I give you, let's say, a graph of who is friends with whom on Facebook, find the largest set of people who are all friends with each other. Okay, a huge number of optimization problems like this that involve satisfying a whole bunch of different constraints actually turn out to be NP complete, which means that again, asking whether any one of these problems can be solved in polynomial time is the same as asking whether all of them can be, which is in turn the same as asking whether P equals NP. Okay, so there are what are called reductions that let us take one of these problems and encode it using another. Okay, so in particular, the traveling
But does
sales.
that require a perfect solution? Does that require
Oh,
a perfect
okay,
solution
good.
to
So
the
okay, so
problems?
So there's a whole theory of approximability and inapproximability that's developed since the 1990s. And so what we've learned from that theory is that for many NP-complete problems, even finding an approximate solution would already be NP-hard, right? So sometimes you can get very quantitative about it. So for example, there's one of the most famous NP-complete problems is called 3-SAT, right? It says like you have a bunch of yes or no, Boolean variables, and then you have a bunch of constraints that can involve 3 variables each. Okay, and your goal is to satisfy as many constraints as possible. A constraint might be like either this variable is true, or else this one is true, or else this one is false, something like that. Okay, and so it's pretty easy to satisfy a 7/8 fraction of the constraints, right? In fact, if you just set all the variables randomly, then you will satisfy like about a 7/8 fraction of constraints on average. Okay, but now a very deep theorem that was proved in 1997 says that if you had a polynomial time algorithm that could satisfy even slightly more than 7/8 of the constraints, like let's say 90% of them, and it could do that reliably, could do that for any instance, then that would mean P equal to NP. Okay. So sometimes we know these inapproximability results. In other cases, for other NP-complete problems, you actually can get like arbitrarily good approximations, but it just the running time for any desired level of approximation, it will remain polynomial, but it will blow up as you want your approximation error to go to 0. Okay, so here, it can be a different story for different NP-complete problems. And this is still a huge topic that people work on, trying to understand. Okay, but when I say, that a problem is NP-hard, I just mean it is NP-hard, to find, whatever solution I asked for, whether that's an exact one or an approximate one, right? So again, if you could take any NP-hard problem and solve it in polynomial time, then that would mean that all problems in NP were solvable in polynomial time. That would include finding proofs of theorems. That would also include finding optimal sets of weights for training neural nets.